Hello, it's Mr. Layman. I'm coming at you today to teach you physics, and I'm doing it on Zoom. I don't usually do things on Zoom, so we're going to do this in one big, long, giant take. So I don't get to do any fun edits, but I also don't get to mess up like I kind of just did right there. But anyway, today we're talking about physics. This is the eighth grade and high school class. This is the Unit 3, Section B, Power and Complex Machines. So let's do it. Um, I do want to talk about a little bit of a review from last time because there's two words that are going to come up very frequently in this lesson. And if you weren't here for the last one, you're going to be a little lost. So, number one is a joule, not the kind that's on a ring. Oh my gosh, I wish I had a prop with a joule on it. I don't. Anyway, not that kind. Joule is a unit related to energy or work performed on a system. So basically, like the amount of energy it would take to do something. We measure that in newtons. We measure the distance that something travels in meters. A watt is a unit of power or the rate at which energy is consumed over time. So, like, how much energy is being used while doing something for an amount of time is a watt, as opposed to just the amount of energy it would take to do something at all is a joule. I think a good way to think about this relationship is to think about it like this with these cute, fun dogs. One way to think about it is like you are measuring power. Think about it like a meal. The joule is the meal. Like, how much energy are we talking about? A watt is how like quickly I'm consuming this meal. By consuming, I might also mean burning off this meal. I can see that we have some dog food and a dog eating the dog food. Actually, it kind of looks like, oh, I was going to say it almost looks like lo mein, but it's dog food. In this instance, you're talking about like something's getting fueled up. Just the gasoline itself, it does not represent joules. So in terms of like, that's why I just left the gasoline there. Like, you're not really burning it off at that point if it's just gasoline like sitting in a gas canister or something. But I do see two other dogs. One is taking a nap, one is running around with a ball. The one that's running around with the ball burning off energy faster, so that one's consuming more watts. Now granted, they might have had the same amount of dog food, but one of them is going to burn off that dog food a lot faster. A big meal is more energy, and like me like running around and lifting weights and playing tennis and things like that would burn off that food faster, requiring me to replenish that energy. There's a big giant chart on the next page, so I'm just going to scroll right on down. All right, so power is work divided by time, how much work got done over an amount of time. I don't mean work like me sitting here like I am technically working. I mean, I guess if my fingers are typing, I am technically working. No, I'm actually working because I'm using some kind of energy. But in this instance, we're talking about work like force and distance over an amount of time. The time we measure is in seconds. It's not hours or years, it's in seconds. The force we measure is in newtons, which is about the energy it takes to lift a lemon, is about a newton. Distance is measured in meters. So I don't care how far it is, just measured in meters. And a joule is 1 newton moved 1 meter. So if I move a lemon about a yard, not across the yard, if I move a lemon about 3 feet or 1 meter, that is a joule. A watt is 1 joule moved like per second. So if I do it in a second, that is a watt. There's a review question from last time. It was on the bottom of the sheet. We might have gotten to it. We might not have gotten to it. You might be encountering this for the first time and be like, I don't even know what you're talking about. Cool. So my question is, it's a very basic math question. How much work would it take to move an object requiring the force of 5 newtons and moving it 2 meters? What about that object requiring the force of 2 newtons and moving it 5 meters? Spoiler alert, those are the same number. Why are those the same number? Oh, you might go, Mr. Layman, it's multiplication. If you multiply two numbers together, it doesn't matter what order you multiply them in. 5 times 2, 10, is the same as 2 times 5, 10. Okay, so I do 5 newtons times 2 meters, or I do 2 newtons times 5 meters, and I get the same answer. Cool. I get, can I type on here? There we go. I get 10. Okay, 10 what? because it's science and I need oh my gosh, I just blanked on this. See, this is where I put a cut. I need whatever the variable is. I need the scientific, not scientific notation. I need the unit. That's it. I need the unit it's measured in. There we go. So is this watts or joules? Well, I'm not mentioning a like amount of time. So in this instance, and I also mentioned in the question, it's going to be work, not power. So in this instance, it is 10 joules. So the correct answer is joules. I am aware that this would be a lot more helpful if watts was work. It's not. All right, let's do problem number 2. That's a fancy car. Vroom! Oh, wow, this car has a lot of horsepower. Horsepower is an actual unit of measurement. 1 horsepower is 746 watts. So 1 horsepower is the equivalent of moving 746 lemons 1 meter in 1 second. Okay. That actually, you know what? Now that I think about it, I don't think I've ever said that out loud before. That actually does sound like the amount of energy that 1 horse could probably pull. So, okay. But this car moves with a force of 25,000 newtons. It moves 100 meters in 6 seconds. Vroom indeed. So, how much power is that? All right. Well, if I go up here to my formula, I can see that the force is in newtons. Cool. And I've got newtons right here. So, cool beans. Yay, newtons. You know what? I'm going to highlight anything I've added in gray. It moves 100 meters. Okay. In 6 seconds. Okay. So we're doing, this is I'm going to actually change this to also gray just to keep it consistent. There we go. All right. So I'm just going to use my formula up here. Okay. So I've got work, which is force times distance. The force is newtons. So 25,000 newtons times the distance. It's 100 meters. Cool. And it's going to do that in 6 seconds. Okay. So I would take 25,000 newtons and I would multiply that by 100. So the first thing I would get is the total up here of like work that's done. So my work in this case would be 25,000 times 100. Yeah. Okay. So 2,500,000. What is this? Joules? Yeah, joules. Okay. So, but that's not the answer because we're talking about how much power is that. Okay. So I've got my time down here over 6 seconds. So I would divided by 6 seconds equals, I did the math earlier. So this would equal 416,000 watts. Okay, but how much horsepower is that? Because if we're measuring this in a car, we're talking about horsepower, and cars are sold like, oh, this car has like really good horsepower. Okay, well, how much is it? So in this case, I'd want to find out the horsepower. So I would take 416,666 watts, and I would divide it by this to get the horsepower. I would divide it by 746 watts. So I would divide those two numbers together, divided by 746 watts. And so how much horsepower is that? Again, I wrote this down earlier. It is 558. 558. It's like 0.58 or something like that. Horsepower. Which for a car with those kind of pipes sticking out of it, that sounds about right. The car that's here is a machine. Machines work to make something more efficient. Let's say you have this pile of dirt. Okay, it's pretty simple. It's outside and you want to move the dirt 10 meters to a garden that your parents want help with making. Okay, cool. What are some ways you could move the dirt? Well, you could move it with your bare hands. You could move it with some sort of machine. You could probably move it with other stuff. I would say my bare hands are probably not going to be as efficient as something like a bucket or a shovel. But those are all different kinds of forms of machines. You also might have listed something like a wheelbarrow that could do it because I didn't say how much dirt are we talking about. And 10 meters is like 30 feet. So that might be a little bit of a distance. Okay. And it might be uphill if it's anything like my mom's place. When I go back there over the summer, she's always got me to, she's always got me there to do a whole bunch of yard work that she saves up all year. So I get to do that with my summer vacation. Anyway, it's only like 95 degrees and the humidity is 80%. It's perfectly fine. Anyway, so those are examples of machines. The shovel, the wheelbarrow, a bucket, any of that stuff. But you also might have listed something like maybe a truck, because if it's a whole lot of dirt, okay, let's move it in a truck. Maybe a bulldozer, maybe even a leaf blower. Okay, any of that stuff. It's probably going to be faster, but it is more efficient because now you're getting into the sense of uh, I'm aware that work is happening. What's the most efficient way of completing this task? Because I don't necessarily want to always be using a machine if the power required to run it is too much. Let's put it like this. Um, Trader Joe's is right down the street from me. It's a 3-minute walk. I'm not going to go down and get in my car and drive to Trader Joe's, which is like a 20-second drive, and then have to find parking. It just seems like an inefficient use of the time. I could probably walk there in the amount of time it would take me to drive my car out of the parking garage it's in. I gotta wait for the gate to open, then I gotta drive there, then try to find parking at Trader Joe's, then park the car, and then it's like it seems like it's not actually any faster. Because if this pile of dirt is like a handful of dirt, I can just scoop it up and go. I don't need to like turn on a bulldozer to do this, right? It might not be as efficient by using these kinds of machines. And if you use a leaf blower, I mean, you're going to move the 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 dirt with the leaf blower to probably work. But if it's to a garden your parents want you to help make, it might not arrive at the garden very effectively, is I guess what I'm saying. It might just fly everywhere and make a big giant mess and require more work to clean up. I mean, I could move a pile of Legos with a leaf blower too, but that might not be the best option. It's less work for that one task, but now there's probably a bunch of other tasks that I'm having to do to clean up as the Legos scattered by the leaf blower now need to be put away. If the task is to clean up Legos, not just remove them, you might have created more work, and don't do that because it's less efficient. Doing this just moves the leaves. If you're spraying around a leaf blower like this, you're just moving the leaves around. They're still there. You're not raking them up and putting them in a bag. You're just blowing them around. It doesn't really help. Machines change one of the following three parts of work: the amount of force you need, aka force, the distance that the force is exerted, aka the distance, and the direction of the force, the direction. So one of those three things is changing, at least one of them. You can have multiple of those changing, but it's got to be at least one of those. For example, if you want to throw a tennis ball really fast, I mean, I could throw a tennis ball, but if I want the tennis ball to travel fast, not just throw it, if I want to have it travel fast, I will hit it with a racket. Using a racket like this can easily launch a tennis ball over 140 miles an hour. That's fast. It's significantly faster than I could throw a tennis ball. If you don't like tennis, you might have played baseball before. If you really want to launch a baseball, you do not throw a baseball, you hit a baseball. That's going to make the baseball go a lot farther. In that instance, if it's the baseball and the bat is the machine. In this instance right here, the tennis racket is the machine. It makes it easier to make the ball go fast. So, AKA, I've increased the amount of force. So I'm increasing its speed and its velocity. Okay. I can make it go farther. So that's a distance. So the amount of force that I've exerted on it is high enough that it not only goes quickly, it goes farther, but also the balls change in direction. If you hit the ball to me, I'm going to hit it back and it's going to have the direction is going to change. In this case, you return to the other player, or I don't know, you hit the tennis ball really hard and it flies out of the whole court. But let's use some math to show our work with some of these simple machines. Okay, so here we can see we're changing the force. Both people need to move an object. Okay, fine. But the person pushing it up the ramp is using work because the distance of the ramp is longer than just lifting the thing up. So pushing in this case is easier than lifting. Granted, I can see that the like ramp option, if I'm lifting the thing and I only need to move it 200 meters, granted, I'm sorry, 200 meters. If I only need to move it 2 meters, granted, it is going to take, it's shorter, but in this case, the work itself per second is going to be easier. It's going to require less power. So here, the total work, oh, you're putting all this extra work in. Right. But this means I just need to travel farther, but it is significantly easier to push something up a ramp than it is to lift it up something. But that doesn't necessarily mean that in this case it's requiring more power. In fact, it's requiring less power. The work is easier. This does mean you need to go further distance with less force. This is sort of like the assembly behind a screw top bottle. Like I have a screw top bottle on top of this. So if I this is not good when it's against the black like that. Okay, so if I unscrew it, oh no, I have to screw it, like I have to turn it a couple of times and it'll come off of there. Fine. But the distance is spreading out the amount of work and force and effort that I have to do. So I don't need to drastically increase the amount of force I need to use. I don't need to like rip the top off the thing when I can just twist it. It is making it significantly easier. Those of you who have canned food at home, you can use a can opener to try to like cut open very easily. Use a can opener to slice open the top of the can, or you can try to use one of those old can openers where you had to punch a hole in it. Oh my gosh, it's a huge hassle. It's so much easier to do this kind. You are increasing the distance, but the force over that distance can be lower, and I can still increase the force higher. Changing distance is also something we see a lot. Chopsticks are a good example of this. You close your fingers a little on one end, and the chopsticks on the other end are a lot larger. So you're getting a lot more of that distance is being closed. You're going to have to use more force because the distance is longer at the end where the food is, but chopsticks are designed so that you don't crush your food. Nail clippers are the opposite. Nail clippers, you increase the distance on the end where your fingers are, and the distance is much smaller on the clipper end. It's so much smaller on the clipper end. And so that distance is smaller, that force is increased. You'll notice in this case, I've increased these to centimeters. So yes, the joules must be in meters. Me dividing them by 100 right here is to get that to meters, because even if it's in centimeters or if it's in kilometers, I'm going to need to adjust it so that it's back to regular meters. The nail clippers move a smaller distance, but also have an edge on them, meaning the force is increased over a smaller distance. This is sort of like saying it's very easy for me to cut a piece of paper with scissors. It's not easy for me to cut a piece of paper with my actual fingers. It doesn't work that way. I can't cut it that way. Doesn't work. Changing direction. This is how a lot of construction is done, especially if you're looking at something like a crane. People might set up a pulley if they need to lift something heavy up into a building. They can pull down on the pulley and the object is lifted up. In this case, you can see that there is, the more pulleys I use, I can amplify this force. But in this case, I'm pulling down and the object is moving up. So I'm changing the direction. This is a form of work. Here you might be saying, okay, the object is being pulled up and like someone pulling it is the like downward force to pull the object up. Most pulleys operate, especially if you're looking at something like construction, you'll have a whole bunch of pulleys kind of daisy chained together, because the more pulleys I use, the fewer joules it will take. but it will take twice the amount of rope. If I use 2 pulleys, it means that twice the rope is being used, but half the force. So that's good for me because I only have to use half the force. So if you were pulling down with the strength of 4 pulleys, you would increase the amount of force you're pulling by a factor of 4. So it's like 4 of you pulling down. So it's really effective to reduce the amount of work that you have to do, as long as you can still maintain the amount of force that you need. So you can increase the force you use. You can decrease, or the distance the force is exerted can change, or the direction of force. A pulley is using usually 2, but I guess you could use all 3 if you want to increase the amount of force that you could use. You also notice that when you have something like a tennis racket or a baseball bat, you're hitting it with the sweet spot of the bat. So further down the bat or the tennis racket you hit it with, the farther it will go. Actually, that's not 100% true in tennis. You want to hit it in this string area. But in either case, that's part of a lever. I'm inferring that we're going to be talking about simple machines next time, like levers and pulleys and screws, like the screw cap on the inclined planes and things like that. Like this is an inclined plane. We're going to talk about that next time. But we call this mechanical advantage. How much the machine changes the amount of work you have to do. A mechanical advantage, really like it. It's just the output force divided by the input force. If the input force, like mechanical advantage, all it is if it is over 1, you're getting mechanical advantage out of it, and you should continue using that machine for whatever task you're doing. If the input force is higher than the output force, you're kind of inefficiently doing something, and you probably should stop. When you increase the force on something like a can opener, let's say you turn with the force of 10 newtons, but the can opener puts a force of 30 newtons on the can, because when you have a can opener, you like squeeze it like it's a pair of scissors, and then you turn the little knob that slices into the steel. Cans are not made out of tin. Mechanical advantage, the output force is divided by the input force. Great. In this case, the input force is, I guess I should put the output force first, which is 30 newtons is the output force divided by 10 newtons. So my mechanical advantage here is 3. Mechanical advantage is 3. Cool. When you increase the distance on something, like my friend Sheena pulling on this rope attached to this lever and being really far away from the truck, you can lift it. So you are increasing the efficiency of your mechanical advantage by being farther away with this lever. If you had a really, really, really big lever, excuse me, if you had a really, really, really big lever, you would be able to move just about anything. The output force here, if I'm closer to so you see these numbers right here. It says times 1, times 2, times 3. So this is the amount of effort it would take to move it from certain areas. She's able to lift this whole truck because she's all the way on this end. She can't move when it's at number 2, twice the amount of effort because she's teensy. And she cannot move it at all on number 4. I can move it on number 2, but I can't move it on number 4. This is sort of like, again, hitting it with the baseball bat. You want to hit it towards the end of that lever, not towards where your hands are. In this case, the output force is 50. The input force is 25 newtons. So mechanical advantage 2. When you increase the distance, it makes the work be less over a longer distance. I did not write that very well. It makes the work, what does this even suggest? Just remove it. Curious. There we go. Makes the work. When you increase the distance, it makes the work less over. Okay, that makes sense. It makes the work less over a long distance. Fine. When you're changing direction, it's always a 1-to-1 ratio. If only the direction changes, then the mechanical advantage is 1. Here we see somebody lifting weights. 200 newtons down, 200 newtons up. Simple. That's 1 pulley. If we gave this guy 2 pulleys, his mechanical advantage would be 2 because you're pulling down, and you'd have to pull more rope. The distance would increase, but you would be pulling with twice the force. We're going to talk way more about things like pulleys and levers and such in our next class. This feels like a good place to stop. We will do simple machines next time. I hope you have a super awesome, cool day. I'm Mr. Layman. Take it easy. Bye.